the Bayes theorem, so an important theorem in math, there's a whole category of statistics called Bayesian statistics that's all about using this formula. But which way does the formula go? And you can mix it up one way or the other way. So 14 out of 19 people said it should be the probability of A on top. And presumably when I hit the bottom, it'll be the other one, probability of B. And I think that's correct. That's how I do it as well. Reveal correct answer. Yeah, so most people got it right. The way I sort of remember is the probability of A is what we are actually calculating. So the probability of A has to go on top. And so really you can think of the probability of A given B if you just rewrite it a different way. Here's yet another way to think about it. Let's get our blackboard going. And this is where we left off with last class, was the Bayes theorem over here. But you could also rewrite it like this. The probability of A given B, you start with the probability of A, and then you multiply it by the probability of B given A divided by the probability of B. This is an equally good way to think about it. And what this is saying is the probability of A given some new information to B, well, it's whatever the probability of A was before, but then we kind of change the probability of A by a factor, which is the probability of B given A divided by the probability of B. So if the probability of B given A divided by B is much bigger, if this is much bigger than the probability of B, then the probability of A given B goes up. So in other words, if you see something, you see B given A, right, so B is what we're given, right? So you observe B, and if B given A is much more likely than B happening on its own, then the probability of A goes up, right? This goes up relative to what it was before. And vice versa, if you see something, if the probability of B given A is much less than the probability of B, then the probability of A goes down. So sort of like you are adjusting the probability up and down based on how big this number is. So this is like a factor to adjust the probability of A based on the evidence. Based on some people like to say this is how surprising B is. So that's one interpretation. If B is a very surprising thing, you see some weirdo event. You're walking around the halls of the building, and you hear in the distance, you hear hooves. You're like, whoa, there's not supposed to be hooves inside the math building. That's super weird. So the probability of having hooves in the building, given that there is a horse in the hallway, that is quite high. So this factor is very high. And then you say, wait, I thought there were no horses in the math building, but now I think there is a horse in the math building. You could also say, well, maybe there's a zebra in the math building, and then you'd have to do a calculation of horse versus zebra. But the more surprising the thing you do, the more you update your probabilities. So the probability of seeing a creature with hooves in the math building is quite low, but if you hear hooves in the hallway, then the probability goes up a lot. Okay, so that's my spiel on Bayes' theorem and how to think about it. We're going to use it today a little bit like we kind of said last class, of trying to think of classifying. So we have multiple classes, and then we have some evidence, and we're going to try to use the fact that we can figure out how each class leads to the evidence and try to reverse it to try to do classification. So we're really going to do what we talked about last time. The probability of class K given X, that's what we want, and we can figure out the probability of X given class K. Okay, so for us, we are going to do the probability of class K given observation X. So we have X's, and we want to figure out what is the probability our observation belongs to class K. Well, this will be the probability of class K, and then we're going to do this conditional probability, the probability of observation X given class K divided by the probability of observation X. So in other words, we need to do this. And by the way, we can do one other thing to rewrite it, which is another common way things happen. Class K times the probability of the observation X given class K. Given class K. If somebody asks you what is the probability of observing some observation X, and there's different classes, then there's sort of more than one way this probability could have come out. it could have come out from any of the classes. So we're going to sum from I equals 1 to the number of classes, n classes, and we're going to do the probability of class I times the probability of the observation given class I. So in other words, when we get some observation x, we see some data x, and we're trying to predict the class, we can figure out the probability of the observation given any individual class, and then add up over all the classes to get the probability of seeing this x. So this is another common way to do Bayes' theorem. We're going to have some more examples with 2 classes. Maybe the 2-class version is worth writing down. In fact, I think in my examples, I have 2 classes. The classes are called orange and blue. Well, let's get some orange in this. Can I get some orange? Okay, so the probability of the orange class orange given observation x, it's going to be the ratio of 2 things. Let's put the equal sign down here. Probability of this class times probability of x given plus the probability of this class times probability of x given, and I'm going to fill these in now. Okay, and I have orange. Let's do orange. The orange is the fun one. Orange, 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 and orange. And we also have another class, blue. Blue. So in this example, the categories are orange or blue, and to figure out the probability of orange or blue, we break it up like this into sum of 2 classes, and generally you have some number of classes. Okay, that's the general idea of what we're going to try to do. Any questions or comments at this point with the overall high big pictures? We're going to get into specifics of how to do it. Okay, that's the Bayes' theorem. The key thing that we got to do is we got to figure out this guy, the probability of x given orange. So this is the new problem. We have reduced the original problem to a new problem, which is how to estimate the probability the class is orange given x, and the probability the class is blue given x. What are these things? So you're given some x value, and you have to tell me what is the probability that I have it the other way. This is what we really want, and I just spent all this time saying, oh, we can flip it and get this other thing, but now I want the other thing. Okay, great. Good. I have it in reverse. So this problem is supposed to be easier than the problem we did, but it's still nevertheless a problem. So the class is orange, or the probability that it's x given the class is blue. And the issue is, what do we do to do this? Question marks all over the board. And to make it sort of concrete, let me show you an example of some blue and orange points. So here we go. Let's turn this on. Very nice. So I got some blue and orange data points. And I'm doing 0 if it's blue and 1 if it's orange. And so in this example, I have like 6 observations. 1, 2, 3, 4, 5. So there's 6 observations in blue and 5 observations in orange. And these are the x values on the x-axis. So there's when x was minus 1.5, we got an orange point. I don't know, how do you want to, what example should we do? Should we do orange and blue, or should we say they're like, this is like how long you studied for the test, and then this is like, did you get a good grade, right? No, this is did you get a bad grade, because if you didn't study, you got a bad grade. Okay, we have some observations here, and we got to come up with a method to figure out, given these observations, use these observations to come up with the probability distribution of x for the oranges and the probability of distribution of x for the blues. And how would you do that? That's the question. I will let you think about it. This is a great sort of thing to puzzle on, where if I just tell you the answer, I think it won't be as good. But I will let you think for a few minutes, and then you give me some ideas, and we'll take your ideas. So how do you estimate the probability of x for the blues and for the oranges? Once we know how to do that, we can combine them to get with Bayes' theorem to get the discriminator. Okay, I'll let you think for a few minutes. Feel free to chat with your neighbors. There's many different possible answers So once you kind of have a feeling for the possible things you can do, you'll have too many answers. You'll be like, I can do this or this or this. But I know when you're starting out, sometimes it feels like I have no idea. But think about it. You have these this little data set. What would you do? Okay. I'll put that there so you can think. Okay, I only have 7 answers. Who needs more time to think? Okay, let me give another minute or two. I will say that there are some methods we've talked about earlier in the course that can be applied here. They were sort of applied in a slightly different context, but if you understood the general idea, you can apply it in this situation too. Let me bump this up to 1:30. So it's you don't have to reinvent the wheel completely to do this. Okay. All right, there's like 30 seconds left. Even if you don't know, just put an I don't know. Or whatever weirdo idea you have is even better than I don't know, because I like funny ideas. There are many different things you could do to try to estimate the probability density given some data. Okay, let's see what people said. What ideas did people come up with? We have this cool little word cloud over here. Okay, let's see. So we have some words like threshold. So threshold, again, is going to be what we're going to do at the very end of this. So our whole game is first we figure out what we're doing now. So first we figure out the probability of the x's for each class. Then we invert that using Bayes' theorem to get the probability of each class given the x's. And then we can say like, oh, we should say that we should classify it as orange when the probability is above 50%. So the threshold idea is that. I mean, obviously they could have written something other than threshold, but the word threshold on its own means that. The probability of class given x's is the thing we're trying to find. And right now we're trying to solve a simpler problem, which is find the probability of x given the class. So maybe somebody wrote probability of x equals. There's something called naive Bayes. And naive Bayes, let me write down what naive Bayes is. let's write down what naive Bayes is. Naive Bayes lets you upgrade from multi-dimensions to from one dimension. Naive Bayes solves the probability of x, the vector given the class, using the probability of x, the scalar given the class. So in other words, the naive Bayes method is a method to estimate the probability density of vectors and multi-dimensional things if you know how to solve the probability of just a single scalar component. So maybe I should write what these are. This is a scalar, also known as an R-valued random variable. And this one is a vector. This is a R to the n valued random variable. So saying let's use naive Bayes doesn't actually solve this problem, right? Naive Bayes says we can, if we knew how to solve this one, then we could upgrade it to vector valued. But right now we're just in scalar valued, right? We only have one x in our little Desmos demonstration. We've only got one x. So naive Bayes is not solving the problem. Of course, naive Bayes plus the other stuff we're going to do will be a nice solution and is solving this problem. But it's kind of, we want something more fundamental than naive Bayes. Okay, let's, what else do people say? Method, P class. Ooh, I'm seeing nearest neighbor. And nearest neighbor is one that you can do. Let's write down what nearest neighbor is. So the straight nearest neighbor, the straight nearest neighbor, let's call this nearest neighbor, well, or we can even add a k. K nearest neighbor, let's call it k nearest neighbor density estimation. Right, so before we had nearest neighbor classification, nearest neighbor regression, you average the values of the people around you, and we had nearest neighbor classification, which is just like which class are you in, but we can also estimate the probability or the probability density, and it would just be something like this. So the probability of x given some class, so what is the probability of x for the, let's say the orange class, you could write it like this. You could say the number of neighbors that are orange, Could you do this? No, I'm getting mixed up. Let me see what other people wrote. I think I might be sort of assuming something. Before I write something else that's wrong, let me actually read the submissions. Okay. So lots of good ideas. Yeah, nearest neighbor. Okay, so there is nearest neighbor. K nearest neighbor is averaging. Okay, here's the problem with this thing. Is if I'm just looking at the oranges, I want the probability of x given the class is orange. This is something we should be able to do with only the orange points. So here I have oranges and blues, and nearest neighbor is something like, hey, there's two guys that are blue close to me, and there's one guy that's orange, so there's more blues than oranges, so this should be blue. But the thing we're trying to do is just something about the orange class. We're just trying to figure out if the orange class, where is it likely that the orange class is? Where is it unlikely that the orange class is? So actually, this nearest neighbor framework, the thing I was going to write is not going to be right. So let me put a big X on it beforehand. I was going to write something like this: the number of neighbors that are orange divided by the number of blue neighbors. And I'm going to do the math thing of NHB is a neighbor that are blue plus the number of neighbors that are orange. This is the kind of thing we did before. But this is all wrong because I want to just use the orange guys. I don't want something that depends on the blues. I want to just have it depend on the oranges. So this nearest neighbor thing doesn't work for density estimation. This is wrong. You cannot do this. But you can do something extremely similar, which goes by the name kernel density estimation. Kernel density estimation. And I would say this is very much like our nearby neighbors. So they're not the nearest, they're nearby neighbors. And this is very much like what we did in the first few weeks of class, where instead of looking at the three closest, we look at everybody and we just weight by how far they are. Okay? So the idea is the probability of x given the class is orange it is a sum over all the orange points. So sum from I equals 1 to the number of orange points. And what we're going to do is add up a little probability density that is the difference between the point xi and the position x. So this is where we are, and we're going to add up. This is going to be like a little window, scaled window, based on the location xi. And the thing that we use to combine these things is called the kernel. So we use some kernel. Sometimes it comes with k. And this is the kernel in kernel density estimation. So this is a very standard technique that is really closely related to nearest neighbors, but is not quite. And the reason it's nice is it doesn't depend on blues versus oranges, right? It's just, we just look at the orange data sets, and it's really how close are you to given orange points. I'm going to show you what this looks like in a second. Let me write down the kernel that we're going to use. This is, you could use any kernel you want, but the kernel that is most typically used is the so-called Gaussian kernel, which looks like this. It's a 1 over square root of 2 pi sigma squared e to the minus x minus y squared over 2 sigma squared. Yeah, okay. That's the one we're going to use. This one is a little nice bell curve shape like this, where the difference is x minus y is the height you're at. So this is x minus y. So if x minus y equals 0, that's the biggest value, and other values are smaller. Okay, let me do one other thing. I'm going to, instead of adding it up, I'm going to average it, and I'm going to show you in a picture what this looks like. So let's go back to Desmos, and let me pull up my little things over here. So the kernel density estimates, and this S value is the sigma in the formula. So my keyboard doesn't have a sigma key, but it has an S key, so I used sigma. And here are the little kernel density estimates. Okay, wait, hold on. Before we do this one, can I get the individual? I want to get the little individual peaks. Here's my data. I want to show the little peaks. Let me see if I can find the peaks. Okay, we're gonna do it by hand. Okay, I'm just gonna write down this thing instead of doing the mean. I just want to plot it. Let's see. I want those little peaks. Okay, great, beautiful. In green here, let's make them blue instead of. Okay, so what is going on here? You'll notice there were 6 blue points, and on top of the 6 blue points, I have drawn 6 blue functions. Let me make them a little more narrow. These functions are the functions k of x, xi. If I make this more narrow, you will see what's going on. Let me zoom out a bit, or let me divide it by 6. That's a fun idea. Okay, so I have these 6 blue functions, and they're centered around the 6 blue points. So there's one centered here, peak centered around here. There's one centered here, a little bit to the right of it. There's another one, and then there's 3 more over there. Those are the 6 blue functions. This is exactly a plot of the individual functions k, x, x. Let me go k of x, xi, for I going from 1 to 6, the number of orange points. I'm doing blue points first, but it's no different. It's those individual things. And you can think of this as like a little fuzzy dot. So the data point that I got was x equals 0.5, and I'm taking the point at x equals 0.5, and I'm sort of spreading it out with this little shape. And I have this for all of my data points. So 0.5, a little over 1, 1.5, all 6 data points. And the kernel density estimate says, look, if you just average these, that's a pretty good estimate. And that's what this function does. So mean of this function that I copied over here is copying it. Okay, so what does it look like? It looks like this. Why does it look like this? Well, this one was sort of on its own, so you average this one with the other ones, not much changes. But these ones all got combined into one big peak. And what this is saying is, look, we saw 3 data points over here, so this must be quite likely for the blue values. That's why we get a nice high peak over there. Then there's kind of no points for a little bit, so the probability goes down. And then there's 2 points over here, so we have a peak over here. And then we have 1 point over there. Is it making sense? Okay, some people are nodding. There is one thing that should bother you. And it's the same thing that bothered me for weeks at the beginning of class that we spent weeks on at the first few weeks of class. What can I change in this thing? What is up to me to decide in this thing, in this estimate? What is something you could tweak a little bit, and it's kind of a question, did I get it? Did I get the setting of it just right?
Kernel?
Say that again?
The kernel?
The kernel, yes. Okay, this is a great point. So I chose this Gaussian kernel. You could pick a different kernel. Another common one is the top hat kernel. That's sort of flat at the top, and that would be sort of more nearby neighboring. And that's saying spread the point out exactly a certain distance. So this is one thing, you must choose the kernel. You must choose the kernel. This is a choice. Okay, why do people like the Gaussian one? There are some circumstances in which the choice of the Gaussian kernel is motivated by the central limit theorem. So if you think your x values come out of a process that is adding up a lot of things, this Gaussian one is good. This is motivated by the central limit theorem. So it sort of has some justification. All right, CLT for central limit theorem. Another choice people use is the top hat kernel, which says it is 1 if x minus y is less than some distance. I think we call that delta. And it is 0 otherwise. So this is 1 if x minus y is less than delta, and 0 otherwise. Okay, and then you have to, it's important that your kernel adds up to 1. So the integral of all the possible values under your kernel should add up to 1. So to make this one add up to 1, I have to divide it by 2 delta, 1 over 2 delta. So it's 1 over 2 delta. So that's another choice. You could do that one. And on the face of it, it's not clear which one is better or worse. And there maybe there's some circumstances where the kernel, you can find some clever choice. But okay, let's pretend for now we're using the Gaussian kernel. There is still, even knowing that we're using the Gaussian kernel, there is still one other choice to be made, and it is on here somewhere. There's a choice to be made in my list of parameters. Yeah. What was that? Sigma, exactly. Sigma. So that's what we called S over here. Right now I made it 0.05, so it's saying that the sort of typical width of this peak is 0.05, but nobody says it should be 0.05. You can make it bigger or smaller, so maybe we'll make it a little bit bigger. And so now this one is a little bit bigger. It's bleeding over into this one. All 5 of these things have combined into one giant peak. Maybe that's a little bit of a better estimate. Okay, but why stop at 0.17? Why don't we go all the way to 2? Nice. They've all combined into this super flat thing. And now I'm just saying there's sort of a blob of the blue things here. And who is to say if the 2 is better or the 0.05 is better, right? How would you tell? This is a question that we covered in the first few weeks of class. So you could, if you wanted, separate the blue points into a test set and a training set, estimate this curve with the training set, and then see how well is your density estimate doing on the test set, right? So the idea of figuring out the optimal value of sigma is a hyperparameter, just like everything else we do in data science. You would check it by some kind of experiment to see is bigger or smaller better. You could also do some theory that says it should depend on the number of points. The more points you have, the smaller you can make sigma. The less points you have, the bigger you need to make sigma. So it is kind of a thing you're going to have to figure out is what is the right size. I'm just going to eyeball it. I'm going to say, so this is, if you can see the individual peaks, I think that's way too small. It's sort of saying that it's really unlikely to have a point in between these two guys because there was one on the left, one on the right, none in the middle. So, but that seems wrong to me. Like that seems like overfitting to the points. If I make it really big like this, that seems like underfitting to me. I think we can be a little bit more nuanced in where we think the blues are. There should be more blues over here and like less blues over here. This is saying they're about equal. I think that's underfitting. So I should probably go somewhere in between. Maybe something like this. I think that's pretty good. So it's saying the blues are most likely to be here, and there's like a little bit of chance of having a little bit on the left. There's not many to the right. So that's pretty good. I like that. 0.25. That's a nice round number. Any questions or comments about how I made this funny blue curve? That's called kernel density estimation. This is a common acronym. People call this KDE. So if you see KDE, now you know what KDE means. Really common way, given data points, to summarize the data as a density. Okay. Now, of course, that's for the blues. You do the same thing for the oranges. So let's turn on the thing for the oranges. That's this one. And we have some other function for the oranges. Now, the oranges have sort of two peaks over here because there's two data points there. So it kind of makes me think that maybe the width for the oranges should be a little bit bigger. There's no reason the width for the blue and the orange should be the same. You can make them different. In this one, just for simplicity, I made them the same. Maybe I'll make it a little bit bigger. Something like that. I think that looks pretty good. So the blues are more likely to be over here, the oranges are more likely to be over here. We have achieved the goal of estimating the probability of the oranges and estimating the probability of the blues. All right, fantastic. So now we go back to our little thing, and we say how to estimate, and we go and we write answer, use KDE. This is like option one. Option number one. We're going to see some other options in a minute. Use KDE. Okay, and if you use KDE, now you have these things, and you can combine them. You plug into this formula, and the formula will tell you the classifier, the probability of being class orange versus being class blue. I'm just going to plug these formulas in, and that looks like this. Let's go to the formula. Okay, so that's the kernel density estimate. And so I call this thing a kernel density Bayes discriminator. Bayes discriminator means I did the Bayes trick on the kernel density estimate. And I'm allowed to pick the probability P of the zero class. The zero class is the blues. And the formula looks like this. So it's F0, the blue density curve, that's F0, times P, divided by F0P plus F1 times 1 minus P. So in other words, I'm using the Bayes theorem. This is the formula we had before, where I put in P's for the probability of blue, and I put in 1 minus P's for the probability of orange. And if you plot this, it will be a number between 0 and 1 that tells you what is the chance. Let me, before I do that, let me just slightly change this. I'll make these areas so we can see it a little bit more clearly. So those are the kernel density estimates. Now this will be plotted as an actual function. This function is supposed to be the probability of a given x value being either orange or blue. I guess because it's a blue on top, this is the probability it's a blue point. So we're hoping the probability of a blue point is large over here and small over here. Let's see if it works. Okay, there's the function. Let's turn on, well, okay, this is 1 minus the function. So the orange curve is the probability you're orange, the blue curve is the probability you're blue, and it kind of does what we want. Over here, you're much more likely to be orange. Over there, you're much more likely to be blue. It all makes perfect sense. So this is combining the formula exactly like we said before. Let's see, can I fit it all on one screen so we can compare and make sure we did it right? So here's the formula we had before. So it's the probability by Bayes theorem, it's the probability of the orange class. That's what I called P, times the probability of x given orange. Okay, I'm doing it with blue. I should have written blues everywhere here. P is the probability of the blue class, so F0 times P is the probability of blue times the probability of x given blue, and then you divide by the sum on the bottom, and then the orange is the reverse. So there you go, the orange and the blue. So this is the Bayesian way, given a kernel density estimate of the densities, to turn it into a classifier. Very nice stuff. Great method. Any questions or comments about how this thing works? Okay. I will tell you, why don't people do this? How come we don't just stop the class here? This method is great for one-dimensional data, but just like we saw earlier in the course, it does not scale well into high-dimensional data. And the reason is, when you have high-dimensional points, you're unlikely to have lots of points that are close together, right? The points are sort of spread out in high-dimensional space, and so this kind of kernel density thing doesn't work very well. People normally use kernel density estimates only in one dimension. It's great for illustrative purposes. If you understand what's going on, you will understand the other methods really well, but people don't use it in real life in high-dimensional things because it sort of doesn't scale to high dimensions well. But it works really nicely for this kind of thing, so this is a nice classifier. Okay, so now that we've done that one, we're on to option 2, which is do something. What else could we do? And again, we're just going to go back to the sort of drawing board over here. How are we going to estimate these two numbers? And we're going to have a different option. What I call option number 2, in no particular order. And let's see what else people said in the mathematize. So there are some other good ideas there. Okay, option 2. All right. So some people are saying Gaussian method, Gaussian method, Gaussian method. So Gaussian method, well, you might pronounce it as Gaussian, depending on where you're from. It is kind of vague, because the thing we just did, you could say that is a Gaussian method. So use the kernel, that is the Gaussian kernel, then do kernel density estimate with the Gaussian. But there's another way you can use Gaussians, which is estimate the entire distribution as a Gaussian. Estimate the entire distribution, and I'll put entire in quotes or underlined, P of X given class, I guess I'm doing it with blues first, class blue equals some Gaussian. Sometimes in probability, you write these little tildes to mean make it like a Gaussian. So you'll say Gaussian with some mean and some sigma squared. So in other words, before I had the little individual points, had a little Gaussian kernel, and I added up the Gaussian kernels over all the individual points. And now I'm saying take all the points together as a whole and try to fit one single Gaussian to the entire thing. So both of these you could say are a Gaussian method. This one, all together, this entire method is called the linear discriminant analysis. And we'll see what's linear about it in a minute. And it is a Gaussian method in that the entire distribution is fit as a Gaussian. Okay, so that's the idea. So in other words, instead of having in my little picture over here, right, how did I make these little blue mountains and orange mountains? I added up a bunch of little Gaussians, right? I added up the 6 blue mountains. Instead of adding up the 6 blue mountains, you should just make one blue mountain that matches all the blue points. Okay, so let's do that instead. So I'm going to turn this one off, and we're going to go from there. So let's turn this off and turn this off. And now we're going to go to the Gaussian density estimate, which is let's make one blue mountain for all the blues. And here's the blue mountain and the orange mountain that I made. How did I make these? I just took the mean of all the points. So if we peek into the formula, I just set the mean. I took the mean of all the x's, and I put that in for the mean. So there we go. Let's do that. So set match the means. And so if you match the means, then you get the mu equals the average value of the xi's. Okay. You could also do a similar thing for sigma. You could make sigma the variance of all the xi's, but instead I just set it to some value like we did before. So I just set sigma arbitrarily like we did before. So in this situation, I have this value r, and I just set the sigma value to r, and I get these two beautiful bell curves. One bell curve lives around the oranges, one bell curve lives around the blues, and you can make them narrower or wider depending on what you want. You'll notice the blue is set to the average of all the blue points, nicely in the middle. The orange one, you might look at those points and think something's not quite right. Does that bother anybody else? That the orange one is I have this orange thing over here, and it doesn't seem to be in the middle of the orange points. What's up with that? Because is the formula wrong? Let's check the formula. So the formula is over here. It's the mean of all the x1s. So it should be the average of the points. Why does it look like that? Well, I tricked you. Haha. There's a point all the way over here. Look at this point. Remember, I said there were only 5 oranges. There's a 6th orange all the way over here that has been living there the whole time. And so this orange curve really is in the middle of the oranges, but it is being sort of affected by this point over here. So this point over here is pulling the whole mountain towards it so that this mountain can live in the middle of all the orange points. I'm trying to show you that the way we're doing it now is sort of more affected by outliers than the way we did it before. So the way we did it before, we had these little mountains around all the points, and there was a little mountain around this guy, but it didn't sort of affect things too much. In this situation, the effect of this guy is to pull the entire thing to the left. May or may not be a good thing, depending on what you're really doing, but it does matter, so be aware of that. Let's go back and let me show you what the other one looked like with this. So really, when I was doing the thing before, there was a little bit of a peak over here, right? So there was a little orange peak over here that I didn't show, and I should have shown. But the point is that this peak only has size 1/6, so it doesn't affect things very much. Whereas in the other situation, it pulls it also by how far away it is. So here it sort of only matters it's 1 point out of 6, just ignore it. On the other one, it's 1 point out of 6, but it's really far away, so it has a big impact. So there you go. Yeah, so this point literally made like no difference for the discriminator, right? When we're trying to figure out the probabilities, this point is already extremely likely to be orange. So having a point here doesn't really change anything, but it does matter in the other situation. So that's what I'm trying to show you with this weird outlier point. Okay, let's go back to what we're doing over here. The Gaussian density estimates. They really are in the middle. It's just that the middle is pulled by these outliers. Okay, so now we have the two curves, nice symmetric curves, an orange and a blue. And then we do the same formula we did before, right? Which is the Bayes theorem. So Gaussian density Bayes, this time I called it Q. Why did I call it Q? P was taken already, so it's called Q because that's the next letter. And it's the same formulas as before. So the density of the zeros times Q divided by the sum of the two different ways to do it. And you get a nice discriminator. Let me make these areas only so we don't get confused on which curve is which. And now let me turn these curves on. So beautiful, beautiful, nice discriminator. You have the orange mountain, the blue mountain, and then you do the ratio, and that gives you this nice discriminator. And it says, for example, this point in the middle has a 50-50 chance of being blue or orange. This point over here, when x equals like negative 0.1, is like 75% likely to be blue. And then as soon as you're like at x equals 0.5 or further, you're just like overwhelmingly likely, 99.9% chance to be blue. That's the discriminator curve given by the Bayes theorem, starting with the two mountains. Okay, so overall, this is doing the exact same thing, just a different way of estimating the densities. Any questions or comments? All right, I have a question for you. This blue curve and this orange curve, they seem oddly familiar. They're quite nice, and they look like something we've seen before in the course. What do they look like to you? That's my question. Shape of the linear discriminator. What kind of shape/function does the linear discriminator remind you of? And the linear discriminator is exactly this funny curve. Where did it go? Here it is. Say this blue curve. That's the discriminator, and people call it a linear discriminator for a reason we don't know yet. It's the discriminator. What happens when you use Gaussian things for both? Okay. What does it remind you of? What does it look like? That's the mathematized question on the table. I will let you think for a minute. Feel free to chat with your neighbors. Feel free to flip through your notes and try to, maybe there's a picture of that curve somewhere in your notes that you can find. Okay, 30 seconds left. If you have no idea, you've never seen this thing before, that's okay. You can answer honestly, but maybe a few people remember what it is. What does it look like? Okay, let us see what has been said. Ha! The biggest word on here is the word I was looking for, which is sigmoid. It is a sigmoid. If you remember, the sigmoid function is the function 1 over 1 plus e to the x. That's the sigmoid function. Okay, I guess this one is going the other way. So you put in a minus sign. Okay, the blue curve now is like that. So the blue curve is kind of like a compressed sigmoid, right? So the regular sigmoid is the purple. The blue is a kind of a compressed one. Could we compress this one a little bit? Well, let's try compressing it. How could we compress it? Let's add a little parameter. Let's do A. Is A taken? No. Okay. We'll try to increase A until they match. That's about right. Look at that. Beautiful. So A equals 10. Oh, nope. Gotta go a little bit bigger. Maybe 12. Let's make our upper bound 20, and then we can slide it around. Okay, that looks good. Look, now they have the same shape. So the purple was the sigmoid. Now it's the sigmoid of something times x. This is the sigmoid of, we've applied a multiplication to the x value before we put it in the sigmoid. I'm going to wait a second. This one goes through 50%, like we said before. This one goes through 50% here, a little bit to the left. Maybe I should subtract off something. So let's subtract a little bit. What should we call the thing we subtract? Let's call that b. I don't know. X minus b. And we'll add a slider for b. Okay, now we can change b to slide it till it's just right. Okay, how about like that? Okay, so there we go. I set a to 15.7 and b to negative 0.15 to move it to the left by 0.15. And now look at that, they line up perfectly. Well, okay, not quite perfect, but the shape is exactly right. This fact that it's a sigmoid is why it is called the linear discriminator. You apply a linear function, that's what the a's and the b's do, to a sigmoid, and you will get the same result as if you had done the whole rigmarole with the Gaussian densities and so on. That's why it's called a linear discriminator. Let's write this down. So here's a fact. Doing the Bayes discriminator, using what? The probability of x given the class. Let's say class K is the mean of class K. Mu K equals the mean of class K. And the same sigma squared for all the classes. Oh, let's write that down. That's an important fact. With sigma squared the same for all classes, it gives the probability of being in class K given x. It turns out to be a sigmoid function, and then in here you have a linear function of x. Linear function of x. So you can write it as ax plus b for some a and b. This is why people call this whole game, they call it a linear discriminator, because after crunching through all the stuff you get, it was just the sigmoid function applied to a linear thing. This is extremely similar to what we did earlier with logistic regression. You'll remember in logistic regression, it was also the sigmoid of a linear function, right? It's just how we were estimating the parameters there, we were sort of doing it directly. In this one, it comes out of estimating these means. Let's see why this is true. So we're going to just do a little bit of a unpackaging of why. But why? Why is it like this? Well, remember the formula for the class. I'm going to do this simple case. I'm going to let's assume all classes are equally likely. So it's 1/2 times the probability of x given class 0. Let's do class 0. And then 1/2 times the probability of x given class 0 plus 1/2 of the probability of x given class 1. So I'm going to just assume for now that the probability of each class is 1/2 of each class is 50%. And why is 50% so nice? Well, it should be 50% and 1 minus 50%. But in this case, 50% and 1 minus 50% are equal, so they all cancel out. This is why I made this nice choice. The 1/2 factors all cancel out, and so the Bayesian classifier says what's the probability of x for class 0, then divide it by the sum of the two probabilities. And in our case, each of these is a Gaussian formula. It's this formula, 1 over square root of 2 pi sigma squared, and then you have e, I'm going to write the e is an x minus 1/2 x minus the mean of class 0 squared divided by, and then we're going to have this thing again, and then we're going to have a copy of it with a mu1. So it's 1 over square root of 2 pi sigma squared. We got an e minus 1/2 x minus mu0 squared again, plus the reverse with a mu1 x minus mu1 squared. Okay, very nice. And already this should remind you a little bit of the sigmoid function, right? The sigmoid function is sigmoid of x is 1 over 1 plus e to the minus x, or e to the x. And it's not 1, it's an e to the x on top, okay. So look, this is kind of similar. We got e to the x's over here, we got e to the x's over here. What don't we have? Well, the sigmoid has a 1, we're missing the 1. And this is the thing that should boggle your mind. I said it was a linear function of x. Here, these are all quadratic functions. What's going on? Why is it quadratic functions here, but it's a linear function there? Well, let's solve one mystery at a time. How can we make the 1 appear? Let's make this number into a 1. To make this number into 1, I'll just multiply everything through by this thing. So I'll multiply the top and the bottom by e to the plus 1/2 x minus mu0 squared divided by e to the plus 1/2 x minus mu0 squared. You see, I'm multiplying by a fraction that is equal to 1. It doesn't change the answer. But the plus here is going to cancel the minus there, and then the exponents will add, and then I'll have an e to the 0. And e to the 0 famously equals 1. So that'll be nice. The other thing you might notice is these factors, because I chose them to be all the same, all cancel out. These cancel out. Okay, and then there's one other thing, which is I forgot to write the sigma squared here. So let me add the sigma squares that I forgot. 1 over 2 sigma here, 1 over 2 sigma squared here. And this is just the formula for a Gaussian, which we wrote the formula for a Gaussian somewhere on the board, didn't we? Yeah, here it was. So I forgot this little factor. Okay, let's put it over here. Okay, sigma squared, sigma squared, sigma squared, sigma squared here, sigma squared here. And now the magic happens. This multiplies this. That becomes an e to the 0, which is 1. So we have equals something divided by something. We have an e to the 0. And it was cooked up to be an e to the 0 because I put a plus here and a minus here. Over here, I'll have minus this thing plus that thing. Plus the exponential. And again, I can factor out all these common factors at the beginning. 1 over 2 sigma squared. And then I'll have x minus mu1 squared in brackets minus x minus mu0 squared. Okay. Divide those through. So this guy and that guy combining, and then same thing on the top. Hey, wait a second. This number and that number were the same number. So when this guy got an e to the 0, so did the guy on top. Well, that's lovely. X of 0 again on top. So the only thing that matters, all of the horrible messiness has just come down to the difference of two quadratic equations. These quadratic equations, these are the log likelihoods of the things. These are the log likelihoods. So we could visualize this difference on the board in our graph. Let's see what it looks like. So I have a little thing set up over here. So again, where are we? Got the blue and the orange, and I can draw their log likelihood over here. Their log likelihood is L0 and L1. Those are the log likelihoods for the blue and the orange. Remember, a Gaussian curve is e to the minus x squared. So you take the log likelihood, you just get minus x squared. Minus x squared, this is what you do in grade 10 when you study quadratic equations. They're just quadratic equations centered around the mean, right? X minus the mean squared. And the thing we care about is the difference between the blue and the orange, right? So the orange is some quadratic equation, the blue is some quadratic equation, and they're just shifts of each other, and we care about the difference. Let's do the difference. D is the difference. Whoa! this is a fun fact. Orange is a quadratic equation. Blue is a quadratic equation. What is the difference of the origin in blue? You might say, hey, that should be a quadratic equation, but it is not. It is a linear function. The blue curve minus the orange curve equals the green curve, and the green curve is linear, and that is because the x squared part cancels out. And you're left with this green curve. You might notice the green curve, it goes through 0 exactly at the point where the discriminator is 50%. So going through the 0 here is exactly the 50% mark over here. Let's see that. So here's this is the linear part. The quadratic term cancels out. Okay, this is a good test if you're a mathematician at heart. If you get excited by the quadratic term canceling out, you're probably a mathematician. Okay, x minus mu1 squared minus x minus mu0 squared. I claim the x squareds cancel. Let's expand this one, expand that one, and the x squareds will cancel. We've got x squared minus 2 mu1x plus mu1 squared. Then we have minus x squared plus 2 mu0x minus mu0 squared. And look, boy howdy, x squared and minus x squared. They cancel out. Amazing. So what are we left with? There's some constant factor mu1 minus mu0. The dependence on x is linear. It's linear. There's x, and then it's the difference between the mu1 and the mu0. Not only that, there's a factor of 2, and there's a factor of a half over there. Those will cancel out. So what do we end up with? We end up with 1 over 1. Those are the e to the zeros. And then we're going to have an exp. And we're going to have minus 1 over sigma squared. And it's just going to be the difference of the mu's. Mu1 minus mu0. Mu1 minus mu0 times x. It just depends on that. Did I do something silly? Okay, plus mu1 squared minus mu0 squared over sigma squared. And that is what we originally claimed. We said that it is a linear function, and then we worked it out, and it really is. It's the sigmoid, and then it's the sigmoid with a linear function. The quadratic parts canceled out. That's why it's called linear discriminant analysis. And it turns out the only thing that matters is x to the left or to the right of the midpoint between the means. So you can do a little more simplifying if you want. More simplifying possible. I will not do that in the interest of time. Simplifying possible. And if you do the more simplifying, you will see that this line actually crosses x equals 0 exactly at the midpoint between the blue and the orange. So this green line, that you do the sigmoid of the green line, that will give you the discriminator, and it's exactly hitting 0 at the midpoint between the two means, the mean 0 and the mean 1. We can also double check. I think I have one more thing on here, which is I did this thing just like I said. If I did, that's the purple one. I want to do this one. Yeah, there we go. So m of x is the sigmoid, or the reverse sigmoid. And then if you do m of d of x is the orange, m of d of x in the dotted green is exactly doing the sigmoid applied to the green curve, and it exactly gives the orange curve, just like I showed with algebra on the blackboard. Okay, so that is the linear discriminant analysis. Now you know why it's called linear. Now you know how it's related to the kernel density estimation. Extremely similar, and they work very well in 1D. Any questions or comments about this one? There's another one that was brought up in the videos, which is quadratic discriminant analysis. So this is another one you can do. Quadratic discriminant analysis, which sounds like it's way more complicated, but it's actually, remember, a miracle happened and the quadratic term cancels out. Quadratic discriminant analysis is what happens when you live in sad land and there is no miracle and the quadratic terms don't cancel out. So all you have to do is use a different variance for both. Let me show you what that looks like. I'm just going to go in here. So let me turn off this whole log likelihood thing. And I'm just going to use a different R for each of them. So here I have R1, and right now they're both equal. So R0 and R1 are equal. But what let's make R1 twice as much. So the orange points are more spread out than the blue points. So the peak for the orange is spread out, and the blue is more concentrated. This kind of makes sense because the orange point, remember we had the point way over here. So the orange points are more spread out. It's a reasonable thing you could do. And you get something very similar. But now the discriminator is not linear. If you do this thing, it is a sigmoid, but not a sigmoid of a linear function. It's a sigmoid of a quadratic function. Quadratics, as you know, are significantly different than linear functions in a number of ways. One thing, this quadratic function is positive over here and negative over here. But quadratic functions, if they're positive over here and they're negative over here, they're going to do something interesting way over here. Does anyone know what a quadratic function would do if it's positive on the right side of the screen and negative in the middle of the screen? What does it eventually have to do on the left side? It's going to be positive again. Okay, let's zoom out and see if your prediction happens. Aha! You see this? So over here, you get this funny thing, and this is a thing that happens in quadratic discriminant analysis. Because the oranges are so spread out, if you get a point at x equals 6, it is more likely to be an orange point than a blue point. And that's because the oranges are so spread out. So quadratic discriminant analysis has this funny like on and off situation that did not exist in the linear discriminant analysis. If you never see any points over here, of course it doesn't matter, but this might bother you, and indeed it bothers me. So the quadratic one, it has this feature, quadratics go positive, negative, positive, and therefore your classifier will flip-flop multiple times, which can be quite annoying. So watch out for that if you do quadratic discriminant analysis. It will flip-flop on you because quadratics go up and down and up and down. Okay, that's something to watch out for. Of course, you can do everything we just said. You can do in one dimension, it's totally fine. You can do it in multiple dimensions as well. And I made a little 3D plot. So here I have 3 classes. I got the orange class. Whoa, that's too fast. Let's go slow. Let's do a nice slow spin, please. There we go. Okay, so we got the orange class, the blue class, and the green class is very weird and new. So we have 3 classes now, and each of them is sort of modeled by a Gaussian distribution, but because we're in multiple x dimensions, x1 and x2, the green class has a really big correlation between x1 and x2, and that's why it's kind of an ellipse in a certain direction rather than a circle like blue and orange. And you can see there's quite a bit of overlap. So there's points in the middle where we're not really quite sure, is it more likely to be a blue point or an orange point or a green point? So these are the little distributions that I made, and they're all quadratic equations with exponentials that are all Gaussian distributions. You can make a classifier in the same way we did before by doing ratios of them. So if you wanted to do orange versus blue, this is the linear discriminant analysis, is a nice thing like that. And you can make classifiers that go 3 ways. Let's see, I thought I had some 3-way classifiers on here. Yeah, here we go. So here's the orange. If you do quadratic discriminant analysis, you'll say that the orange is the most likely to be over here or over there. Those points are likely to be orange with these like funny planes where we're switching from we think it's orange to not orange. Let me turn on the other ones as well. I think we got to turn off some of these distributions or we're going to have too many things on the screen. But the final classifiers look like this. So there we go. There's a region of space where we think they're blue points, but it's split into 2. Blue is here and here. Green is down the middle, and orange is there and there. So this is what quadratic discriminant analysis looks like in many dimensions, and it looks quite funny, sort of from the top. You've split up space into these funny areas, and because of the way quadratics work, you can have multiple areas for each one. So that's quadratic discriminant analysis, which is like linear discriminant analysis, but kind of more annoying. Okay. Questions or comments about any of that? So let's write this down. Use a different variance for each, and then I'll say warning. Quadratics go up and down. Which can be sort of unexpected and annoying. So the final discriminator is sigma of some quadratic equation of x. Quadratic equation of x, where sigma is the sigmoid function. Before it was a linear, this time it's a quadratic, and the quadratic sometimes is negative, positive, negative. will be kind of annoying to deal with depending on what you want to do with it. Okay, so those are the three sort of basic methods. I personally love KDE. I think KDE is underrated, and everyone should know KDE because it's so great. And then you have these nice classifiers. The thing I'm going to go back and do right now is something we talked about a minute ago, which is naive Bayes. And naive Bayes lets you upgrade from any individual thing to a vector valued thing. So I'm going to tell you what naive Bayes is. And naive Bayes just has exactly one assumption baked into it. Naive Bayes says, what is naive Bayes? Okay. Naive Bayes lets you estimate the probability, and instead of writing x vector, I'm just going to let me write x1, x2 given the class. Okay. So you have, suppose your data is multidimensional. You have an x1 and an x2, and you want to do it for some class. Let's say class 0. Okay. And naive Bayes says, let's make an assumption. Let's assume that x1 and x2 are conditionally independent. So what is naive Bayes? It is the assumption that they're conditionally independent. Assume x1 and x2 are conditionally independent. In other words, x1 and x2 might be correlated, but the only reason they're correlated is depending on the class. If you know the class, within the class they are independent. And by this independence, you can write down this formula of the probability of x1 given class 0 and the probability of x2 given class 0. So this is the thing. By independence, when we have a multidimensional problem, if we assume independence, then we can split it off as the product of individual things, and then we can apply any method we wanted to estimate either of these. So use previous methods on these. Previous methods on these. Okay. So that's the whole shebang in naive Bayes. And I have a little example for you that I'm going to pull up that I'll just show you quickly of how this works. So this is the Titanic data set. Has anyone heard of, who's heard of the Titanic data set before? This is a really fun data set. It's everybody who was on the Titanic, you know, that boat that sank. As you might know, some of the people on the Titanic died and some of them did not die. The Titanic data set says, can we classify who died and who didn't die based on information about them? And this is the kind of information we have. So passenger ID, that's like their number. Survived 0 means you didn't survive. So unfortunately, Mr. Owen Harris died on the Titanic, but Mrs. John Cummings survived on the Titanic. And we have some information about them, their age, their ticket number, their fare. This is interesting. It's like how much they paid for their fare. Did they have a cabin? If so, which cabin? I also made a feature here called the log fare. So putting this on a log scale. And then this one is really important. What class were they in? Were they in first class, second class, or third class? There should also be, there's another really important one. These siblings are like, did they have siblings on the ship or their parents and so on. But there is one that is quite important, which is, are they male or female? So that one is somewhere in here. And it turns out, basically, a good guess is if you were a female, you probably survived, and if you're a male, you probably died. But let's do it with naive Bayes. So I made some variables. Okay, we're going to get to this curve. We're going to talk about this next class, these kinds of curves. The thing I want to show you today is the naive Bayes. So how did I do naive Bayes? So I have two variables that are numbers. So the two variables I have are age and the log fare. And what I did is I looked within the category of people who survived and the people who didn't survive, and I just calculated the mean and the variance, the standard deviation, for people who survived and didn't survive. So of everyone who survived, their average age was 30 point. Of everyone who survived equals 0, those are people who died. Their average age was 30.6. Of everybody who survived, their average age was 28.3. And 28.3 and 30 are pretty close together, which means that this age thing is not really going to be very helpful for telling it apart. But if I have the mean and the variance, I can draw the blobs, right? I can draw the blobs I had before. Where did the blobs I have before go? My blobs, there they are. Okay. Right? So you can think of, right, I have a mean and a variance for people who survived and people who didn't survive, and I can draw these bell curves using the mean and the variance. And that's what I'm going to do. So for age, thinking of the x-axis as age only, I can draw a blue curve and an orange curve just based on those two numbers that I calculated, the mean and the standard deviation. Of course, what we're saying is that the numbers are quite close together, so it's not going to be super useful for discriminating. Okay, let's go back here. What is more useful is the mean and the variance for the log fare. So the amount of money they paid is 10 to this number. So people who died, they paid like $100 for their ticket, 10 to the power 2.7. But people who survived, they paid like $1,000 for their tickets, 10 to the 3. And this is a pretty big difference. So if you paid a lot of money for your ticket, you were more likely to survive on the Titanic. You were probably somewhere where there were more lifeboats, this kind of thing. The first class cabins were better prepared than the other ones. So the fact that there's the mean is higher for the log fare is going to let me use this to figure out that people who paid more were more likely to survive through Bayes' theorem. So these blobs, these make perfect sense. So these are doing the Gaussian blobs for each of these factors, age and log fare, separately. And the naive Bayes assumption says, look, if you did it for each of them separately, just multiply it together. Just multiply it together. So take what was done for age, take what was done for log fare, multiply the probabilities together. That will be your probability estimate. That's the naive Bayes estimate. In practice, the way this is going to come about is I'm going to actually do the log of the probability, and it'll be the sum of the logs, the x1, x2. So the log likelihoods add the log of the probability of x1 plus the log of the probability of x2. In other words, the log likelihoods add together. The log likelihoods add together. Okay. And of course, this assumption is not completely correct. This is kind of a simplifying assumption, but it works pretty well in practice. Any questions about what I've done so far with the log age and the log, the log fare and the age? Okay, that's fine. The thing where it gets interesting is I have some other categories that are either 0 or 1 value. They're were you male or were you female? You see, that's a great example. Sex male and sex female. So sex male is 1 if you're male, and sex female is 1 if you are female. Of course, they're in this data set they're opposite each other. And I can also treat that as a random variable. It's not a blob. It's a random variable that is a Bernoulli random variable. It has a p-value. So I can do this kind of thing. I can say, what is the probability? I can do what is the probability? So I can have x1, x2, and I can have these are continuous random variables, and then I can have a third one, which is a Bernoulli random variable. Let's call that b1, and b1 is either 1 or 0. So the probability that b1 equals 1 equals something, and the probability that b1 equals 0 equals something. It's some value I'm going to call p, and this one is 1 minus p. And the point is, by doing the naive Bayes assumption, I can just build this in to my thing by just multiplying it on. So it's the probability of b1 given the class you're in. So the nice thing about naive Bayes, or one of the nice things, is that you can combine continuous and discrete things because you're just multiplying them probabilities together anyway. So for each of these factors, I calculated the probability just by counting of all the people who survived, how many were male, how many people were female. So these are people who died, survived equals 0. 85% of them were male, and 15% of them were female. In the reverse, people who survived, it's the other way. People who survived, it's 30% of the people who survived were male, and 68% of them were female. There's these other ones that, like what class you were in, you can also look at that. It's a little bit more nuanced. Let's just focus on male and female for the sake of argument. So I have all these p's, and I have this huge list of things, and all I'm going to do is use this formula. I'm just going to add up the log likelihoods. So just like I did on the board over here, I use these estimates, the p-values, the means, the standard deviations, and I add together all the log likelihoods. That gives me the final log likelihood. And of course, you can do this in scikit-learn automatically, but I did it just in a loop. So I have NLL. NLL, does anyone have a guess? What does NLL stand for? I'll tell you what LL is. LL is log likelihood. What is the N? Negative. Yeah, that's right. So it's the negative log likelihood. And what is the negative log likelihood? I added together the value minus the mean divided by the thing squared. These are the blobs, the orange blob and the blue blob, the Gaussian curves. And then I added the Bernoulli factors. And you might notice this formula. Look at this formula. It's the value times the log p. This should remind you of the cross-entropy loss. So I'm adding together all the log likelihoods, and then I get the probability. OK, we're going to go over what this thing means. There's a video, if you haven't seen it yet, for the ROC curve next class. But this is my final predictions compared to NB stands for naive Bayes, and LR stands for linear regression. And so the linear regression and the naive Bayes are pretty similar. It doesn't do too much different. So this is like plotting what I thought the probability was one way, what I thought the probability was the other way. A diagonal line down the middle means they're pretty similar. So there you go. The naive Bayes is people who actually survive. I think they have a pretty high chance of actually surviving. Because the orange is actually survive. And people who actually died, I think they have a pretty low chance of surviving. So it's pretty good. And the other way you can compare it is by using these ROC curves. That's what we're going to do next class. So that's a very quick example on naive Bayes, which is just combining what we did earlier with the probabilities. You can combine over several variables. The naive Bayes, you can combine a bunch of variables by just multiplying them all together. OK, questions or comments about any of this stuff? You can check this out on the GitHub. Your project 2 will be about this kind of thing, and naive Bayes is one of the possible things you can do on your project 2. Linear logistic regression, LR, is another one you can possibly do on your project 2. Questions or comments? Yeah?
What was the purpose of the Bernoulli?
So the Bernoulli is when I have something that is either 0 or 1 valued. So the x's in the examples we did in class were Gaussian bell curves because they were continuous and they could be any number. But if you have a variable that is either 1 or 0, then instead of modeling it by the mean and the variance, you just model it by what is the probability it's equal to 1. And so I was computing this value of p, and then I was using that formula in my probabilities here. So it's just when you have a variable that matches either 0 or 1, it's more appropriate to use just a p-value, one parameter, rather than a mean and a variance. Yeah. Great question. OK. All right, let's stop there, and we'll see everyone on Monday's class. Make sure you do your peer reviews before Monday. You should have 2 of them to do. Let me know if you have any questions or comments or tech issues with the peer reviews. OK.